Hey there, welcome to this video. We are going to talk about the trapezoidal rule. This is lesson 6-2 and usually an introductory lesson in the integral unit. So we're going to go ahead and jump in. Similar to Riemann sums where we're approximating the area under the curve, but this is specifically dealing with what if we want to get a better approximation and we're not using rectangles, we're instead going to use trapezoids. So let's go ahead and jump in. We've been using rectangles to approximate the area under a curve. However, this is not the only method that we can use to approximate the area or accumulation. Finding that area of rectangles is very easy to calculate, which is a good method to use. However, sometimes it leads again to significant over or under estimations. Another shape that's relatively easy to use, that's a better approximation, is a trapezoid. They're easy to find the area and they often result in a better approximation. Here is a couple of images of a trapezoid. One, we just do the general image of a trapezoid where you have a height and then you have two different bases. Okay, so this is what a trapezoid looks like, and usually for our application, if we're looking under a curve, our trapezoids are really tilted where this height is really our width. So we have equal widths, and you can kind of see that here. So we have two different heights, and so if I want the area of this object, the area is again, it's just base times height, but I have two heights, so what height do I use? Well, you use both of them, you're just going to average. So here's the formula generally that we use: 1/2 base times the two heights added together, okay? And then again, another way that you would see this is again, base times the heights, right? All of this divided by 2, okay? So generally, you know, that's the formula that we're going to go ahead and do, and this will be very similar to Riemann sums. So let's go ahead and look at an example. Here is example 1. They say approximate the integral from 0 to 10 of f of x dx by adding the areas of the 5 trapezoids, and we can see these 5 trapezoids here shown in the graph below. Okay, well, I have these 5 different areas, and so let me go ahead and first set up the integral from 0 to 10 of f of x dx is going to be approximately, and I have a rectangle, not rectangle, I have trapezoid 1 right here, and it looks like this width is 2, so I'm going to say 2 times, and I'm going to take both of my heights, my left height, which is 0 according to the graph, and my right height, which is 4 according to the graph. There you go. And I'm going to divide by 2 because I'm averaging those heights. Okay, so there you go. There's rectangle number 1. Let's look at rectangle number 2. Rectangle number 2 goes from 2, it looks like, to 5, from 2 to 5. So that is going to be a width of 3. And I'm going to average again these heights here. Okay, so height 1 looks like it's 4. Height 2 looks like it's 3. So 4 plus 3, and we're going to go ahead and divide by 2. Okay, rectangle number 3. Rectangle number 3 next. Looks like I have a width here of 1 from 5 to 6, right? From 5 to 6. So 1 times, and then my two heights, 3 and 2. 3 plus 2, and average. Divide by 2. Okay. So again, because I'm multiplying, right, if I was taking 1/2, all of these would multiply together, so I can place them all over 2. If this makes you uncomfortable, you can just place the 2 underneath the averaging of the heights. That's fine. It's the same exact thing. Okay, let's keep going. Plus, I'll put my plus symbol down here. Trapezoid number 4, which actually ends up being a rectangle. So my width here is going to be 2 from 6 to 8. And my two heights are both, again, 2. So 2 plus 2 divided by 2. And you can kind of see how, you know, how the averaging of the heights really, right, works out to what if it was just base times height. Since that is a rectangle, I mean, you could just do base, which is 2, times height, which is 2. So you get 4. Same thing here, right? 2 times 4 gives you 8 divided by 2. You get 4. Okay, so 2 ways that this all works out, okay? And then my last trapezoid here, again, I have a width of 2, and then my height 1 is 2 right here, and my height 2 is 5. So 2 plus 5, and we're going to divide by 2. Okay, there is the trapezoidal rule. Usually this question, if it appears, it will be a portion of the free response question, usually on the tabular form question, and you will not have to simplify this. You may need to pay attention to units, but again, we'll talk units in the future. It could be a multiple choice question where you may have to kind of simplify this and calculate this, but at this stage of the game, we're going to leave this just like this. Okay, here is example number 2. Let's go ahead and look at this one. Use these trapezoids with 4 equal subdivisions to approximate the area shown. And we can see we have a curve here, okay? So I want the area of this. And so, I guess they don't even give me a curve to call this. Let's say this is f of x. So the integral from, I'm starting at 10, and it looks like we're going to 50 of f of x with respect to x is going to be approximately. And again, I'm going to use the trapezoidal rule. So if you want, you can go ahead and you can see if you can get this right without me. You can pause me and try this one and then check, but I'll talk through it right now. So pause me if you want to try it ahead, and then you can, try it, but let's give it a go. Okay, they all have equal subdivisions, so that means they all have the same width, and it looks like by 10. So that's nice. So I can go 10 times, okay, height 1 here, it looks like it is, and be careful. Maybe I was about to approximate. I was like, that looks about 2, but I don't know. Hey, look, they give me a table. Okay, so at 10, it is 1.8. Okay, 1.8. And then at 20, it is 2. Okay, and I'm going to average those heights. So here, if I don't place them all over 2, this is what it looks like. Okay, and then I can do the next one. 10, again, I know my first width is 2, and my next one, it looks like, is 2.5 at 30. Okay, and again, we can average. All right, and then I can go ahead and average my next one is going to, again, be 10 times 2.5 plus the second height up here at 40, looks like it's 3.5. Okay, again, divide by 2. And then the last one, 10 times 3.5, and then at 50, our height is 2.2. Okay, and there you have it. Okay, so did you get it right? That's what it is. Again, if you have to approximate, look at your table of values, see if they give you these values. All right, let's move on. Here is generally what this question will look like on the FRQ portion of the exam, and it'll be a sub-question, usually like part B or something. They give here a table of values. Notice my first row is t values, hours, independent variable, and the output is a derivative, p prime of t. It's a rate, and that is thousands of people per hour, and I have some outputs here. Okay, let's see the context. An amusement park opens its door at 9 a.m., t equals 0. The rate that people enter the park at time t is modeled by the function p prime of t in thousands of people per hour. Select values of p prime of t are given in the table above. Use the trapezoidal approximation with 3 subintervals indicated in the table to estimate the total number of people that entered the park from 9 a.m. to 7 p.m. Okay, so what they do here, again, they give us our A value and our B value, our start and our end, and they say the 3 subintervals indicated by the table. So we know that 9 a.m. is time 0 here. Okay, so I'm going to start here, and then they want 7 p.m. Okay, so if I'm going to 7 p.m., I guess that would be what, 10? So we're going to stop here at t equals 10. They also say 3 subintervals indicated by the table. This is very important here, indicated by the table. So I kind of sometimes like to do this. This would be my first width from 0 to 2, my second width from 2 to 5, and then my third width from 5 to 10, okay? And that kind of also gives us your widths, if you think about it like that, right? Width 1 is going to be 2. Width 2 is 3. Width 3 is 5. Let me put that in red. Is 5, from 5 to 10. Okay, so there's my widths. Now we just need heights. This is a trapezoidal approximation. So here, really, you might use left Riemann sum for a height. You might use right Riemann sum for a height. You might have midpoint, right, where you have to determine the midpoint. Okay, but let's go ahead and do this. So the integral from 0 to 10 of p prime of t dt, the integral of this rate that people are entering this amusement park with respect to time, is going to be approximately, well, for the first 2 hours, because that's what it is, the rate that people entered was 7 plus 11. We'll go ahead and average that. Bingo! There you go. There's your first subinterval. Okay, then from 2 to 5, well, for 3 hours, we started with a rate of 11 people, thousands of people per hour coming in, plus, and then we ended at 8,000 people. So we'll average those two rates. Okay, so we're getting the total, right? The accumulation of people entering this park. Oh my gosh, is it Disneyland? Plus, and then for the last one here, for over 5 hours, we started at 8,000, ended at 4,000. So we'll average those to get our heights. And there you go. That is it. Again, this would be an FRQ question. You do not have to simplify. You do not have to simplify. But make sure, if you do, you remember PEMDAS, okay? PEMDAS. So, you know what? Let's go ahead and let's just practice this right now. I feel like this is simple enough. If not, who cares? Who cares? So, go ahead. I want you to pause me. I want you to try this. Let's see if we get it right. Okay, let's go ahead and let's see if we match. The first one's pretty simple. The 2's just cancel, so you get 18. Here, 11 plus 8 gives me 19. I cut that in half to give me 19.5, and then I multiplied by 3 to give me 28.5. And then here, 8 plus 4 is 12. 12 cut in half is 6, so you have 5 times 6, which is 30. So we can add all of this together, and I got 76.5. Now units, remember when you're doing integral, you're going to multiply these units. So it's not like a derivative where you're dividing, right, to find that rate of change, rise over run. Here you're kind of doing the opposite. You're taking the rate, the rise over the run, and you're multiplying by your independent variable. So this rate kind of goes away, right? So here, this is hours. This 5 is measured in hours, and this 6, right? This is the average of the rate that people are entering the park in people per hour. So if we go ahead and multiply them, the hours cancel. Anyway, we get thousands, not hundreds of people. Okay, so let's look at example 4. I want you to go ahead and read this question, pause me, and then I will talk through it and go ahead and try this. But try this one completely free. Okay, hopefully you are able to go ahead and try this one. This one says the height of a tree at time t is given by a twice differentiable function h, where h is measured in meters and t is measured in years. Select values of h of t are given in the table above. They say use the trapezoidal sum with 4 subintervals indicated in the table to approximate 1/8 of the integral from 2 to 10 of h of t dt, the average height of the tree over the time interval 2 to 10. So what I like about this question is this question has a concept that we will cover later on in the semester, and that is this idea of the 1/8 in the front. Kind of ignore that, but this is taking an average. What I do want to relate to what we are doing today is the integral of 2 to 10, sorry, from 2 to 10 of h of t dt. So just for the setup, this 1/8 is going to hang out front. And I know that might have thrown you for a loop, and if it did, you can go ahead and pause me now and jump back in. But that 1/8 kind of hangs out front, and now we're going to do our general trapezoidal sum. So this is what you should have gotten from the trapezoidal sum, is you should have gotten 1 times 2 plus, sorry, not 2 plus 3, 1.5 plus 2, 1.5 plus 2 divided by 2. That is your first trapezoid here. And then we have our second trapezoid, which has a width of 2 from 3 to 5. And we're going to average the height of the tree from 2 to 6. Plus, our next trapezoid is from 5 to 7. So we have 6 plus 11 over 2. And then our last one, our last distance indicated by the table from 7 to 10 is a width of 3 with heights of 11 plus 15. All divided by 2, okay? So that part is your integral. This is your approximation. Remember, Riemann sums, trapezoidal rule, they're approximations for the integral. So if you have anything else multiplying on, adding on, that kind of stays there. We use these rules to help us approximate area under the curve, okay? Hopefully in this video, give me a thumbs up if you learned how to utilize the trapezoidal rule and how it helps us find the area under a curve. I'll catch you guys in the next video. See you next time.